Okay, in this video we're going to talk about rational functions. Rational functions are in the form of one variable polynomial over another. So we'll have p of x over q of x. What we're going to be doing is we're going to be writing in factored form. We're going to write equations of vertical asymptotes or coordinates of holes that occur in the graph. We're going to write the equation of the horizontal asymptote. We'll find intercepts, both the y-intercept and any x-intercepts, and we'll find coordinates of any place on the graph that crosses the horizontal asymptote, making a rough sketch and plotting additional points if necessary. So let's get started with our first graph. Our first graph is f of x equals x squared plus x minus 2 over x squared minus x minus 6. I'm going to factor this to be x plus 2, x minus 1 over x minus 3, x plus 2. And you can see that the x plus 2's cancel. However, x cannot equal negative 2. And we get x minus 1 over x minus 3. So x not equaling negative 2 means that we have a hole in our graph. So those common factors produce a hole. So let me draw a graph. And I'm going to show you where that hole would be. If I put a negative 2 into the simplified version of this expression, I would have negative 3, negative 2 minus 1 is negative 3, over negative 5, which is 3/5. So at negative 2, positive 3/5, I have a hole in my graph. So that hole is at negative 2, positive 3/5. And this is a 1 right here. Now let's look at x minus 1 over x minus 3. We know that x cannot equal 3 as well. We already know x cannot equal negative 2 from the original, but we also can clearly see that x cannot equal 3. This right here that's remaining is a vertical asymptote, and that vertical asymptote occurs at x equals 3. So this is a vertical asymptote at x equals 3. So it's an equation of a vertical line, 1, 2, 3, which means our graph is not going to cross that line ever. Vertical asymptotes cannot be crossed. I have a leading coefficient of 1 and a leading coefficient of 1. I have a degree 1 in the numerator and I have a degree 1 in the denominator. That tells me that my horizontal asymptote, because I have the same degree, my horizontal asymptote is going to be y equals 1. And that 1 is coming from not the degree 1, but it's coming from the 1 over 1. And that's because they were the same degree in the numerator as it was in the denominator. So degree 1 in the numerator, degree 1 in the denominator. And I'm going to explain what happens when you have different degrees in just a moment. So now I need to figure out what my x-intercept is, my y-intercept. So I've got my y-intercept is going to be the value of y when x is 0. So instead of x minus 1, I'll have 0 minus 1. Instead of x minus 3, I have 0 minus 3. And I have a y-intercept at 0, 1/3. So 0, 1/3 is right about there. I'll have an x-intercept. Let's try that. It's going to be the value of x when y is 0. So x minus 1 over x minus 3. Well, the only way to get this fraction equal to 0 is if the numerator is 0. But if you cross multiply, you'll get 0 times x minus 3 is 0 equals x minus 1. And my x-intercept is at 1, 0. And then what's happening is with these rational functions is we could tell it's dropping. This graph is dropping. It's dropping as it gets closer and closer to that vertical asymptote from the left-hand side. It's never going to cross it, but it's going to just hug it. I like to call it hugging it. It hugs it all the way down. So it's going to hug this asymptote all the way down. And then what's going to happen over here is we're going to get to that hole, and we're going to kind of go around it, you know, kind of through it without including it. But we need to know, do we ever cross this horizontal asymptote? We're going to see that in just a moment. Let's hop over the vertical asymptote, and now we really do have to put in some values. X minus 1, x minus 3. Let's put in a 4. So if we put a 4 in, 4 minus 1 over 4 minus 3, that's going to be 3 over 1, which is 3. So if you put a 4 in, you get a 3 out. Let's put a 5 in. 5 minus 1 over 5 minus 3, that's 4 over 2, which is 2. So you put a 5 in and you get a 2 out. And you can see what's happening here. You're going to hug the graph like that. Now, do we cross the horizontal asymptote? So what is we? We is x minus 1 over x minus 3. Does that cross the horizontal asymptote? What's the horizontal asymptote? The horizontal asymptote is 1. So we'll set x minus 1 over x minus 3 equal to 1, and we'll solve. So let's try to solve. And that will give us the value of x that gives us a 1 as an output. So x minus 1, I'll cross multiply, is equal to x minus 3. If I subtract x, I get negative 1 is equal to negative 3, which is false. Therefore, there's no solution for x. And we won't cross the horizontal asymptote. So I'm going to come back up here to my drawing, and I'm going to continue my drawing to have an arrow and just hug that horizontal asymptote on its way to the left. And that's our sketch. That's our sketch of our graph. Rational functions are interesting. Horizontal asymptotes. If the numerator degree is less than the denominator degree, then your horizontal asymptote will be 0. So y equals 0 will be your horizontal asymptote. We had equal degrees. If the numerator degree and the denominator degree are equal, then the horizontal asymptote is equal to the leading coefficient of the numerator over the leading coefficient of the denominator. So that's what we had in our example. If the numerator degree is greater than the denominator degree, then the horizontal asymptote does not exist. There is no horizontal asymptote. So let's take another example. Make sure you get those down because that's really important for you to figure out what type of horizontal asymptote you have, if any. And let's do an example here. Y equals 2x over 3x squared plus 1. Now I have a degree 1 over a degree 2. Therefore, my horizontal asymptote is y equals 0. The denominator is going to tell me if I have any holes or vertical asymptotes. Holes occur from factors that cancel in the numerator or cancel with the numerator. I'm going to go back here and show you. So in this example right here, we had x plus 2 canceling out with x plus 2. That meant that x equals negative 2 became a whole. We don't have any common factors here. So holes occur from factors that cancel with the numerator. Vertical asymptotes occur from remaining values that did not cancel, that make the denominator equal to 0. So in this case, 3x squared plus 1, there is no real number that's going to make that denominator 0. Anything times itself will be positive. So x, no matter what I put in for x, I'm going to have a positive number times 3 plus 1, which will always result in a positive number. I'll never be able to get 3x squared plus 1 equal to 0. Therefore, there's no, in this case, 3x squared plus 1 will never equal 0. And now I need to put the therefore. Therefore, no vertical asymptotes and no holes. So this is going to be an interesting graph. So what's next on our list of things that we need to find? Well, we need to find the factored form, which is not factorable, vertical asymptotes, none, holes, none. Horizontal asymptote is y equals 0. So let's find our y-intercept next, and our x-intercept, if any. And then we'll see if we cross that horizontal asymptote of y equals 0. So the y-intercept is the value of y when x is 0. So 2 times 0 over 3 times 0 squared plus 1. So that's 0 over 1, which is 0. So the y-intercept is 0, 0. The x-intercept is the value of x when y is 0. The only way to make this fraction 0 is if the numerator equals 0. So that x-intercept is also 0, 0. Well, when I go to graph this, it's going to be an interesting graph, because when I go to graph this, I've got a horizontal asymptote at y equals 0, and I always use a highlighter to graph my horizontal asymptote. And I already am crossing that horizontal asymptote at the origin. So what's happening to the left and what's happening to the right? Let's take a look. We've got, this is actually a really cool graph. I like it. We know that we don't have any vertical asymptotes. So we're going to have to put some values in and see what's happening. It does have a beautiful symmetry to it. Remember that we had y equals 2x over 3x squared plus 1. Let's put a positive 1 in. If we put a positive 1 in, we're going to have 2 times 1 over 3 plus 1. So that's going to give us 2 over 4, which is 1/2. So when I put a positive 1 in, I'm going to get 1/2 out. When I put a positive 2 in, 2 times 2 over 3 times 4 is 12, plus 1 is 13, so 4/13. So not quite as big as 1/2. And then when we put a 3 in, we'll have 2 times 3 over 28. 6 over 28, that's even smaller than our 4 over 13. So what's happening over here is we're going up, and then we're going to come back down. And the only place we're going to cross the horizontal asymptote is at that origin. So when we put a negative 1 in, so now we're going to put a negative 1 in. When I put a negative 1 in, I get 2 times negative 1 over 3 plus 1. Well, that's negative 1/2. And then when I don't know why I did that, negative 1/2 right there. And then when we put a negative 2 in, we're going to get 2 times negative 2. 2 times negative 2 is negative 4. And then when we put that negative 2 in the denominator, we're still going to get a positive 13. So now we're just getting negative 4/13, which isn't as big as negative 1/2. And it looks like what's going to happen here is we've got an odd function. We got some symmetry going on. So we definitely have some symmetry going on. Now, can we look at this function and determine it's odd? 2x over 3x squared plus 1. Well, let's see. 2x over 3x squared, 2x over 3x squared plus 1. If it's odd, we can put in a negative for x. So if it's odd and it's got that symmetry, right, we put a negative in for x and a negative in for y. So 2 times negative x, 3 times negative x squared plus 1. So I've got negative y equals negative 2x over 3x squared plus 1. Negative y equals, I'm going to take this negative and bring it down here to keep everything simple, 2x over 3x squared plus 1. So I have a negative term on the left, a negative term on the right. I'm going to multiply or divide both sides by the negative, and I get exactly what I started with, which means we have an odd function, which means we're symmetric about the origin. And when we look at our graph, that's that beautiful symmetry. The blue is symmetric to the green across the origin. That is our graph. It's actually quite exciting there. Quite exciting. Now there's going to be some challenging problems for you, but this right here is a very good beginning to what it is that you need. And I'll provide some other videos that give a little bit of detail in different areas for you to watch and perfect your understanding.